So the next speaker is Professor Patrick Langdon. Patrick Langdon has been with the university in the department for a number of years. He's now taking a position to be a professor of engineering design in the Edinburgh Napier University. What he's talking about is his work while he was at Cambridge, working in collaboration with Jaguar Land Rover as a CAPE partner, and in developing some fantastic technologies. So without further delay, Pat, maybe you would like to start.
I think it's very great to be able to do this talk, so I'm looking forward to it now. I'll share my screen now, hopefully. Okay, so I'll proceed with the talk. Thank you for the introduction, Ping. I'm very pleased to be able to give this talk because of the great relationship I had with CAPE, roughly speaking, between 2012 and the present day, actually 2020. So it's a story of multiple projects that started some time ago, and the advantages that CAPE gave us in order to be able to do these. So I'm Pat Langdon, I'm Professor of Engineering Design and Transportation. Currently I'm acting head of the Transport Research Institute at Edinburgh and Napier, but for a considerable amount of time, of course, I was at Cambridge. And what I'm trying to do is give you an idea, not just of the technical aspects of the projects, but really almost how the projects were initiated, how they became a theme or a series of themes of research, and how those themes of research are continuing to this day because of the fertile soil, really, of the CAPE arrangement. So hopefully, yeah, so that's the overview of the project. I'm going to talk about a little bit about my background because I think that's important for somebody who's trying to arrange or trying to organize CAPE projects, and some observations on CAPE and how it works. I'll talk about the MATSA project, which I believe is of interest, and the various projects that followed on from it and how they were related in the real world rather than in the world of just purely publications of research. Because of the nature of these sorts of online things, I would encourage interruptions. So if anybody wants to unmute and ask a question during the presentation, please feel free to do so. I won't consider that impolite, as long as Ping is happy with that. First thing to remember from my perspective is that I'm not an engineer. I'm actually a psychologist. I have a degree and PhD in psychology from the University of Sheffield. And I did, that was in object recognition and computer artificial intelligence. And I did a 4-year postdoc in computer vision. In those days, working on neural network architectures to learn the inverse kinematics of a saccade control for these sorts of robot heads. So I had a background in artificial intelligence and neural networks and robotics a long time ago, back in the days, and that is actually a very useful aspect of my background. Also, after starting at Cambridge in 97, I then became part of the Engineering Design Centre, which is another fertile basis for research and an excellent place to develop a research platform. I was involved with many years of methodology research that was funded by the EPSRC. Again, that was an advantage of having a different background in psychology as well as in robotics and engineering. An important project that I was involved with was CAMU, which is regarded as about motion impaired computer users, and I'm going to talk about that in a bit more. And that was a very important antecedent of the MATSA project, so I'll come back to that. But again, that was allowed through the relationship I had with the Engineering Design Centre. And then as time went on till the present day, I was a lead manager and author of the Inclusive Design projects at the Engineering Design Centre, which are concerned with improving design for the wider audience, and of course other aspects of research to do with mixed methodologies between the multidisciplines. So that's the multidisciplinary background, and the reason that's important is because I want to talk to you a little bit about the way in which these projects arose, and also the importance of CAPE to them. So first, in the first instance, you need to have, in a CAPE relationship, a company committed to top quality academic research. And that's important because the members of CAPE are already committed to that, but also it's important because lots of industrial relationships with research universities are very much consultancies, or in fact are not research, they are development. And it's important to consider this to be a research relationship. On the university side, you need a principal researcher, somebody with a multidisciplinary background to be able to not only conceive the projects, but actually manage them and understand the relationships between the different aspects of the disciplines who are involved in the work. Even more important than that, probably, is you need a technical manager and or a supervisor of the work under the CAPE agreement, who has a shared understanding of the different roles of the academic and the researcher and industrial R&D. And in this case, that was true because the main relationship was with Lee Skotchak, who was a R&D human factors specialist with a background in human factors, which of course overlaps into psychology. So it's important also that that individual is persistent, because if they're not persistent in an industrial environment, then there will be a loss of continuity of the research, which is going to be a theme that will come up as we go on. Also, it's important that the persistence is actually a working one rather than just simply a relationship. He and I achieved an agreed understanding about the way we were going to work as soon as we had the idea of which way to pursue the research. And it's important that does exploit the strengths and the weaknesses of each side, the industrial side and I need not say to you, of course, that JLR provided technical lab and staff resources, whilst Cambridge, mostly academic research areas. CAPE is great because it has an agreement to publish, which is also very useful for fertilizing the academic research aspect of the relationship, of the industrial relationship. And finally, before we go any further, it's very important that there's actually a good or compelling research idea that you want to implement and through the CAPE agreement. Why is CAPE so advantageous? Well, there are a lot of schemes around of clubs of various sorts with industrial organizations, but CAPE is a very well organized facilitator for research, and it appears to be able to accommodate relatively short proof of concept projects at a high research level between a partner and a university group, and is therefore very well suited to that in its configuration. A main aspect of that is its configuration as industry friendly, in the way it's organized with relation to management and reporting and so on. Yeah. Budgets, for example, are approved at the start of the project and configured with a contract that's already there, designed for university employment practices. Funding is committed for each year and therefore is able to be guaranteed, research jobs are guaranteed for that period. You can have flexible start dates for projects within reason. It's relatively agnostic with respect to the ways in which the projects are staffed on the university side, which allows for different types of researchers to work on projects at different times. There are easy pathways to patent, which of course is important for industry, especially to Jaguar Land Rover, for example. There's a nice clear direct administration with not many levels to it, which I greatly appreciate, i.e. pretty well direct administration, which is excellent. You don't have to worry about new agreements or new legalities. There are standard rules in place that can be used as a reference point. And it's very flexible with respect to phasing, stages and milestones during the course of the planned research program or project. And that will come up again as it's quite important for the MATSA project. Basically, it's up to the industrial partner as to how they want that to be organized, but CAPE makes it very easy to do that. And this allows for multi-phase and multi-year programs, which is one of the ways in which MATSA was successful in breeding other programs and research areas, which really initially were not conceived of. It's also flexible for start dates, end dates, and most common principal investigators' requests, for example, problems with recruitment delays and extension of project after recruitment. So I'm going to talk about the MATSA project. That's the first project that I started with Jaguar Land Rover and Lee Skropchak. The various people involved include Bashar Ahmad, James Murphy, Simon Godsill, Professor Simon Godsill, and on the JLR side, Lee Skropchak, Rob Hardy, and Eduardo Diaz, who are extremely good collaborators. The MATSA project has a history in assistive technology and disability, and it's important to talk about that because I think this indicates why the project was actually originated, and also indicates the value of having a multidisciplinary background. So on the left here, you have cursor movements of individuals who have cerebral palsy, which is a motor output problem of the human body, which cannot be cured. And so these people live with the inability to motor control their hands or other limbs for movement. If you give them a task like selecting a target on the screen, you tend to get these sorts of traces of their cursor. In some cases, relatively straightforward if they have a mild condition. In other cases, with severe vibrations and overshoots, etc. On the right, you can see that the work initiated in the Engineering Design Centre looked at the ways of compensating for that using mechanical devices. In this case, it's a mouse, which were used in a robotic way to try and apply appropriate resistance or boosting to the movements, therefore helping the individuals. And the results of that was rather successful. So in a standard task where you're on a central point on the screen, top left here, a red target circle lights up and you have to reach it. That's the sort of task that gives rise to those traces we just looked at. On the right, immediate right, top left of those quadrant of traces, you could see that the impaired response can be severely disrupted and overshoot in considerable ways. In many cases, the overshoot is so great that the user is unable to reach the target in order to press and select, even if they could coordinate the selection, which very often they couldn't. It can be a less serious in that case. If you look, if at the lower trace, that's an able-bodied trace, so even that contains some degree of overshooting. And there's a lot of research into pointing devices for this sort of compensation. With the force feedback mechanical system that we use, we increase the usability of the system by roughly 50%, and that's illustrated by the traces in the top right there with one of the most severe participants. So there was a lot of success with the mechanical-based compensation. There was a considerable amount of work around 2003 on the relationship between disability and impairment. And a very important insight that is very important for the development of MATSA is that impairment is actually a scale that varies depending on who you are. It can originate with health issues or healthcare issues, but it can also originate with situational or contextual issues or variables. For example, vibrations, noise, temperature, lighting, and so forth. Any hands-busy situation, such as flying an aircraft or driving a plane, is also likely to generate a temporary disability if the user is required to attend to another task away from the primary control task. So it's very much the case that individuals can be disabled by the technology or the interfaces they are required to use. Of course, that's a temporary dynamic thing. It's not a permanent thing as it might be with some sort of healthcare issues, but it's worth bearing in mind that this was defined as a situationally induced impairment. And that gave me the idea of looking for software-based solutions to the cursor movement problem of people with cerebral palsy or motor output problems. And in searching for a way of processing the sort of data that is on the right of this slide. So this is an individual who's trying to reach the circles see the blue one there. And the main problem is that they are very inaccurate. They vector away from the target, even though they are intending to vector towards it, and they can't control the force of their movement. So they tend to overshoot and then vector again, leading into a sort of cycle of which takes considerable time and is very, very frustrating and disruptive for them. That sort of data is not easily processed, and despite a PhD student looking in that area and many other techniques being tried, I was convinced that a software-based solution was possible. And I ended up in Professor Simon Godstill's office in Corpus Christi with my data set. And literally within 30 minutes, he whipped out a laptop and demonstrated the strength of the sort of approaches that he was using, which in this case was a particle filter approach, I think. And it's clear that is able to, that is straight away clear, that is able to compensate for these sorts of cursor traces and excessive overshoots and so forth. And it has many other advantages as well, as I learned. This led us to describe a potential project where in a vibrating environment, a touchscreen could be used in much the same situation. And that was prompted by the observation that cursor movements in a vibrating vehicle were very, well, not so much very, but were similar, but with some relationship to these disrupted movements from the individuals with cerebral palsy. And so Jaguar Land Rover agreed to look at that when I described it to them, and we started to think about how we might address that issue. Now, there are a number of areas which I'm not going to go into. I just do not have time in this talk to talk about all the aspects of the project. But very soon it was evident that we, rather than looking in a two-dimensional basis, and rather than thinking in terms of looking at the vibrations in the car and recording those and perhaps correlating those with the user's attempts to touch the screen, it became very evident that those correlations were very, very low indeed. In other words, a person's hand or finger in the vehicle in a car does not correlate well in 3 dimensions with the actual screen and vehicle movements. So that being the case, the obvious way to do it is to look at the actual tracking the movement in 3 dimensions as it approaches the screen. And that has the advantage that you can both filter it and also use the Bayesian probabilistic approaches to assessing what the intention of the user is in 3-dimensional space as they move towards the target. We developed quickly an approach to that. That's an advantage of working with a signal processing group who are extremely good at that sort of thing, and developed a scheme like this one here. So you have a gesture tracking device. In those days, it was the early leap motion device. That gives you 3-dimensional information about movement. Using a Bayesian intent system, you assess what the intention of the movement was, possibly with some degree of information from other sources, such as eye gaze or IMU, inertial navigation movement, and we'll come back to that later. But also you require a decision facilitation scheme to decide when the individual really intended to select a point on the screen. And that also is a very important aspect of the problem. So by using that approach and by choosing a selection scheme where the probability, once reached, of around 90%, causes an automatic selection of the screen element, the MATSA project was well and truly underway. And all this occurred within 1 year. And here's a quick video of the early laboratory prototype based on the Bayesian selection process. Let me know if it doesn't work. Of course, the intention was to test that early prototype, early algorithmic approach And of course, immediately we engaged in in-vehicle studies on the Gaydon test track. And I think an important part of this relationship was we were able to do that again within the first 18 months. That's partly accessibility to Jaguar facilities, which unfortunately would not be so easy today with greater security and other issues. But at that time, we were able to set that up within months. And we drove vehicles around, in this case it's a Range Rover, around the Gaydon track with a variety of different surfaces, sometimes a motorway and other times broken paved surfaces and other surfaces. So if we look at the nature of these sorts of traces in 3 dimensions, motorway is relatively smooth, but if you didn't know, there's a great deal of vibration and indeed a lot of jumping and jerking that goes on even on normal motorways or so-called smooth motorways. On the other hand, if you have an uneven road with speed variations, potentially a rough road or an off-road, the sort of cursor movements in 3 dimensions look more like this. So if you look closely at them, you can see that they have the properties of being very often in different directions to the targets than you would expect: jerks, rebounds, and rotations, and spiraling around targets. So that's a relatively difficult task, but is something that the signal processing approach was able to cope with. And the approach is basically a Bayesian one. And in fact, the demonstrator that you saw there uses a nearest neighbor approach. So the intended destination is assigned a probability, and then this belief-based prediction is followed by a classifier in order to decide at what point the probability of every potential target on the screen rises to a sufficient level that it's the one that the user wishes to intends, in fact, to select. Prior information can be used in this approach in the form of contextual information, such as which point you are in the human-computer interface, or indeed other things such as eye gaze and layout and so on. And that's something we might return to later on. There are immediate advantages for using the algorithms that were developed. And in fact, over the course of 2 or 3 years, the MATSA project developed a variety of novel publishable algorithms for doing exactly that. So here we have nearest neighbor bearing angle, which was essentially a benchmark or a straw man algorithm, mean reverting diffusion and other types of diffusion-based approaches. And they're characterized by the fact that they're almost all of them better than the neural network process at around about 30–40%. But in fact, even the nearest neighbor approach is fairly accurate, 60–70% prediction levels, around 40–50% of the movement towards the target. In other words, the system is able to decide the intent of the user not much more than 50% through, and in some cases as low as 30% through the movement, which allows for a very useful approach to use of interfaces, to interface selection. The results of the early work, which was done fairly quickly, showed that the algorithm used were capable of reducing the pointing times by as much as 40%, especially in severe noise situations, but also in motorway situations. And also that the workload, which is a NASA measure qualitative measure of the perceived amount of effort and workload that they're putting into a mental task, was also as much as 50% lower. In other words, it was a lot easier to use the predictive display, and also it was a lot more effective during very vibrating environments. And in fact, that was even using the relatively straightforward nearest neighbor approach. In fact, the best algorithms were not tested at that time. So we know where this has got to now. And so if I show you this video, hopefully you can hear the audio. So I put in the videos actually to some extent to keep people alert, as I know these lengthy talks can be trying. And so that is currently moving through what I would call the technology readiness level. So if proof of concept after about 1 year was TRL3, is now in the area of 5 or 6, and Jaguar Land Rover have taken it on. But the project continued with Cambridge's involvement for many years as part of the facing the challenges, the company facing the challenges of increasing the technology readiness levels of that work. And that rotated about various issues, not simply developing the code, but also making it appropriate to onboard computer capability, and also to configure it for different vehicle cabins and the rather challenging infrared environment in car cockpits. Because of the success of this project, a number of other projects were discussed, and very importantly, the advantages of working with the very advanced world-class techniques developed by the Signal Processing Laboratory by Simon Godsill and people like Bashar Ahmad, in application in other areas were appreciated. And so a separate project was configured called the Driver Intent and Preferences Prediction and Profiling Project. Essentially, the idea is to predict some aspect of what a user might do on the basis of sensor data and other information. It was originally called, here, as you can see here, the BLADIP project, but uniformly everybody hated the acronym so much that it was changed to DIPLAD, which sounds considerably better for some reason. The main JLR partners with this are, again, Lee Scrupchak, but also Dr. Thomas Popham, who is now at Warwick, and Tahid Ardishri, who is interested in the wideband aspects of it. So this project was conceived as a way of assessing or developing or regressing latent parameters, such as intentionality, potentially something called stress, which sometimes is configured in human factors research as arousal levels, but not by me. And also issues such as the underlying latent parameters of cognitive function, such as working memory capacity, for example. So my role here was just to try and bring those additional cognitive and other human factors in as potential latent parameters that were to be developed from the observable research data, from the observable sensor data, and the various factors such as road surface, weather, and passengers, and so on. So by introducing the psychological component, this actually elevates this sort of model from basically a 1960s human factors model to one suitable for the future of cognitive workload. The very straightforward system diagram looks something like this. Sensor data of various sorts comes in. There's a process of data fusion, which of course is an area that signal processing specializes in. Information is extracted. There's a Bayesian inference system. And the idea is those latent parameters are developed in real time and allow decisions to be made in real time. And they affect some, what would have been in the MATSA scheme, a selection scheme, but a selection choice scheme. In this case, it's action assisted. So it's about any potential action that the system would like, that the designer would like to trigger by fusion of data of various sorts. One of the great advantages of the sort of work that the signal processing group do is that they can use advanced statistical filtering approaches to data, and also that very often can cope with asynchronous, noisy, and heterogeneous data. Again, that's a very common sort of data that you get from real applications in real sensors in real vehicles. The application algorithms can be tuned to the environment, particularly the environment of the user, and the learned priors could be used. Those could be priors of various different sorts, as we might look at later. And one strong prior might be something like eye gaze, for example. User experience, experimental evaluation, information about other aspects of the user's environment can be used also to feed into the potential actions that can be taken. it's the nature of these sorts of CAPE projects that it's possible, and certainly this is something we did, to actually divide the project into phases or stages based around the apparent validity and significance of the research deliverables and the research objectives. So this goes beyond a project to a program. And the idea, of course, is that every stage in the future, say to 2 months to 3 months, sorry, to 2 years to 3 years in the future, although there is less fidelity in the research objectives, it is clear that there's directions that are required. And so that allows for projects to evolve during the course of the research program. And this is important because in an organization like Jaguar Land Rover, 3 years is a long time during the development cycle. And there are a great number of changes very often in management profiles and prioritization of technology. And indeed, it's a hard discipline because those management prioritizations reflect hard deadlines in the development process. So if the researchers don't meet them, then they cannot be used in those vehicles, for example. So there is a constant process of management, which means that the CAPE process, which is so well organized around industry, allows for constant feedback to and from between the university and the researchers. And an important thing to remember here is that is likely to generate new projects because of immediate prioritized demand, but it also causes projects to change, not only in the nature of the project, but also in terms of the staffing of the project as the industrial partner reorganizes itself. So for example, here, the DIPLAB project went through a series of different evolutions over many years, and actually each one had various different aims. I won't be able to cover all of them, but I'll try and cover most of them. And in this case also, they transformed into another project relatively recently in 2019 called the Occupant Identity Project. And the staff involved here included Professor Godsil again, Dr. Bashar Ahmed, who's worked through most of these projects, myself, and some researchers such as Jaiming Lang. And on JLR side, new managers and new artificial intelligence experts have taken over project management, so Zuzu, and older ones who we've worked with from MATSA were there for continuity, people like Rob Hardy, and I can't emphasize how important it is to have these skills on the industrial partners side. So one of the focus areas which suddenly became prioritized was, can we use these approaches to decide who's returning to the car when the driver is outside of the car, using information such as mobile GPS, the inertial movement unit inside a mobile phone or in another type of device like a key fob, and possibly also vehicle data from the vehicle. A question that was also raised was, how could we use that information and that data to decide who was driving the vehicle? And again, a number of solutions were immediately pursued by Cambridge. A very successful one was looking at the angle of ingress of the potential user as they approach the vehicle. And that was a very good way of distinguishing drivers because of their orientation of their mobile device with respect to a magnetometer. The also possibilities were use of step or gate detection and the door signals, of course, from the vehicle. That actually did develop quite well, but due to a number of research issues that could not have been foreseen, the focus changed to the use of Bluetooth eye beacons on the handles, on the surface of the vehicle, that were going to communicate with the vehicle using Bluetooth, and that information was able to provide these sorts of sensor data. The idea of that project was to locate them by fusing data from 6 Bluetooth sensors and then estimating range and bearing from the return data. And from that process, if we look at the vehicle here, the sensor data would allow, hopefully, the direction, the individual's target, and they're also whether they were a driver or whether, for example, they were on the off side or the near side of the vehicle. There was some very quick developments in the RF area, which I shan't go into as I'm not an RF specialist, but some emotional issues were immediately applied. For example, it became clear that Bluetooth low energy beacons, which is what was available to us at that time, are not good at propagating through liquids. They're not good at propagating through metal, but they do go through glass very effectively. And this raised the issue of potential occlusion relationships, which are either a difficulty or a advantage that can be exploited. And in fact, that was the main driver of the research, as a potential advantage to be exploited. This led to ground truth data collection. Researchers using a differential GPS accurate to about 10 millimeters and spending time walking around the vehicle and a random walk to enable us to record ground truth data. As you can see, that's a fairly comprehensive route or random walk, if you like, and it actually involved other vehicles. Indeed, my own vehicle was parked alongside for a while, and generated quite a good data set at this point in the project. Here's an example. Here's a series of graphs that reflect fairly typical responses, RSSI responses from the sensors on one, the beacons on one side of the vehicle. That's fairly typical of all the beacons. So each beacon would have its own response, but they all looked much like that. And you'll notice straight away that despite the curve fitting, the regression curve fitting, there is a very poor relationship between range and RSSI. In fact, it's so poor that the inversion data suggests that you could be as much as 30 meters inaccurate if you just use the RSS data in itself. And this isn't necessarily because of occlusion. These sensors are on the side of the user in this case, but they could be due to a number of other issues that are related to Bluetooth low energy. So that gives you an idea of the sort of project that was being carried out. But in fact, that project continued in various different forms for various reasons. Essentially, the research was very good and allowed developments in many areas to approach the same issues over and over again. So there was effectively a relatively longish gaps in the research, but a continual persistence on the part of myself and signal processing to keep addressing the issues with Jaguar Land Rover, and Jaguar Land Rover responding positively to that and trying to organize better relationships. So in January 2019, that's relatively recently, this project re-emerged as the Occupant Identity Program under different management with a big deep learning AI team, Zuzu again. And there were some data collection delays that led to that, but that's essentially a longish interregnum that occurred. The idea, again, was to identify occupants as they approach from their smartphone or device data, determine the location at the earliest possible point using intent and predictive Bayesian approaches, localize the passengers as well during their walk, not using GPS. So the main goal was not to use GPS data, which allows it to be used in underground or urban settings where GPS is poor. And of course, there was various motivations, including preparing the car for arrival of the drivers and passengers, activation of various sensors, including security sensors, and also systems that allowed user to be guided back in car parking areas or guided back to their vehicle. The outcomes of this project are fairly clear. There was a Bayesian inference framework developed and it was designed to be usable with both BLE and also the newly available ultra-wideband technology incorporated into mobile phones. These are very different RF environments, and in fact, that was maximally exploited by the project. The implementable projects allowed real-time algorithmic operation, fusing data from a number of sources and mitigating all the noise and occlusion and missing data effects that we saw just now. And it enabled identification of the user before entry without using any door signals. It also delivered improved localization, and this will be used by JLR in future for future intelligent vehicle services. A real-time demonstrator was an app on an iPhone. There's a significant volume of experimental data useful for future research for RF development, and various, and importantly, journal and conference papers are still being submitted based on the research done in this area. It's worth noting here that COVID managed to disrupt the latter parts of this project by cancelling demonstrators that were going to be made for Jaguar Land Rover in 2020. I think it's probably fair to just have a look at the sort of improvements over the years of the project. So here, on the right, you have the probabilities of the user being arriving at a particular point, back left, front left, or back right. And as you can see, the inferred tracking is significant, and the probabilities were very useful, deviated at well enough in advance in order to allow the vehicle to perform the various tasks. So relatively successful, but many years of work and multiple projects were involved in that. And then following on also from the DIPLAD project is a series of other projects, again, under the deep learning AI team, Zuzu, as well as specific interested groups within JLR. There was a need, or a felt need, or a prioritization of learning about users and drivers' activities and various different data sources, and using that to learn, to not only learn, but cause the vehicle to respond specifically to the context of the driving of the user. The idea, again, was exactly that originally stated in the DIPLAD project, infer the driver's latent state. And it was, in fact, a psychological latent state of workload that became quite important, in very important sense that they need to be available to perform some activity or perform some human interface offering from the car at a given point during their driving. And that indeed ideally would be profiled for individual drivers, and also it would be based on driver status, also the context of use, for example, the weather conditions, and the user's response to personalization. So this really is the DIPLAD project from many years before, re-emerging as an artificial intelligence project, looking at how the car can offer different types of human interface to the user without prompting, but with a Bayesian and a probabilistic approach to a number of different sensor data sources. So the team, again, Basha, myself, Jimmy Lang, also Nermin Kaber, a PhD student. And it's worth mentioning that he's from the EDC, and there were a number of PhDs before this that were also associated with these projects. And so CAPE is very good for providing a suitable bed for PhD student research. Professor Simon Godsill, of course, is the main driver of the research novelty. And in the JLR side, it's worth mentioning David Oxtoby and Phil Thomas, who are senior engineers at JLR, who took on the task of developing this research. I'm not going to talk about this in great detail, except to say that it is still ongoing to this day. But the sort of things you can see here is how, for example, workload, which is indicated on the right-hand graph, measured by various sensor measures of the user, of the driver, is related to the inability to recognize and press an interface button. This is not surprising to psychologists. It's a consequence of working memory capacity limitations with human beings, but it's very important if you're going to accurately be able to detect that. If you're going to base the offering of other human interface elements to the driver. So looking very successful and ongoing at this moment to this day, the Smart Cabin project. So finally, I wanted to round up to say, remind everybody of the advantages of CAPE. These are in the brochure, the CAPE brochure. I think it's very clear that a lot of this research would not have taken place without CAPE. CAPE is a facilitator, it's accommodated to short projects. However, as I've just been indicated, it also is it's very well suited to the development of a longer term working relationship with between the industry partner and the researchers. It allows the flexibility of customization of the working relationship, not just for experimental and logistic facilities, as I've said here, but also in terms of management priorities as they change, as the environment of the industrial partner fluxes, then the industrial partner will change its prioritization. And in some cases, that would be the death of traditional research relationships. But through CAPE, it's possible to allow that. And in fact, CAPE is well suited to the rapid startup of projects and the transformation of projects from one area of research to another extremely rapidly, which is one of its greatest strengths. There's an excellent patent procedure built into CAPE, which operated very successfully through all these projects. CAPE is an industrialized collaboration framework that allows a close working environment with regular reviews, meetings, and deliverables. It's also extremely useful for cross-fertilization of ideas and results between multiple projects at the same institution. So, for example, ongoing projects with JLR in the computer lab on visual processing and so forth, or visual of camera images, were running at the same time as this, and there was a great deal of benefit to be gained from those cross-fertilizations as well. Indeed, more projects could have been developed. And the other aspect, of course, is worth noting is that all the solutions developed were all novel in the sense that they were publishable and, in fact, patentable. So the researchers generated a number of patents. MATSA patent is itself probably the most important one. That's the first one, but a series of other patents were filed as international patents were filed, including the object intent patents, which were developed with Mauricio Munoz and Thomas Popham, as well as myself and Bashar and Simon Godstill. You know, it would not be quality research if there were not good research outcomes, including international papers in articles and journals. The one I am particularly pleased about is the magazine IEEE Signal Processing magazine article, which gives a good overview of the entire approach and the people involved with it. But of course, a large number of researchers at various different times have contributed to this research. So finally, to round off, I would say I would thank my main collaborators who have been now Dr. Lee Skrupczak on the left. He's the Jaguar Land Rover manager and still a very excellent contact at JR. Bashar Ahmad, who has been the main key researcher right the way through most of these projects, but most importantly, Professor Simon Godstill, who has provided the anchor of all this research in novel and publishable research. So that is it. So I would open and invite questions.
We would like to thank you for your interesting lecture and invite everyone to ask questions.
Thank you, Denise. One thing I would say, and I think it's worth my mentioning it if anybody is not wanting to ask a question, but there were a number of other projects that were managed during this CAPE relationship. Indeed, there was one project which was even more, I think I haven't got any more slides on it, but there was another project which was based around the future HMI of vehicles that was more focused on inclusive design and human-machine interface research. And that was a very successful project that generated a lot of books and documents that were usable by Jaguar Land Rover engineers in order to improve their understanding of what the likely future of inclusive design in vehicle design of the future as well. And that was managed in all along while this was going on. So there was at least one other CAPE project that I haven't really gone into a great deal of detail on as well.
I think we had someone who wanted to ask a question.
Question.
Thank you very much for delivering the really nice talk. I'm new to Cambridge, new to England, and very new to CAPE as well. So it is great to see, because I'm very interested in collaborating or working with industry to lift some research outcomes to products. So I think what you've shown to me is quite inspiring. I don't really have any technical related question to you, but I definitely look forward to see more work from you. And I really like the multidisciplinary approach for one technique. I just want to see if you have any comments regarding of how to, like, is it difficult to initiate a multidisciplinary, to start a multidisciplinary project, or what are the key things we need to pay attention to when we try to adopt a multidisciplinary approach?
Well, that's a perfect question. Thank you very much, Jenny. That's welcome to CAPE, I should say, if you're new to it. The answer is here, the multidisciplinary approach was led to the project in the first place, because without it, I don't think we would have realized the link between trying to compensate for disabled movement and trying to use a touchscreen in a vehicle that's jumping around. However, as we went on, I think it's very clear that an awareness of other disciplines and the way in which those disciplines treat issues, even the language that they use, is absolutely critically important. And I think it's very important to have other sources of funding, such as Research Council funding, who mostly look for projects with high impact in multidisciplinary and cross-disciplinary project areas. So the answer to that is, I think it's absolutely critical. And I think one of the ways we should change the way engineering is taught is to try and increase the understanding of other disciplines, particularly human factors and let's say human factors, social and other areas. I wouldn't include business so much, but I think that is important too. Thanks for the question. That's great.
Any other questions?
If nobody have another question, I have another one.
Yep.
So this is actually a bit more related with technology. So I see that all the work that have happened here, they're at the technology level. Well, I think, please forgive me if I use the wrong language, because I am from a material science background, so I'm a material scientist.
Excellent.
From my perspective, I always see that a new material always inspires new technology, and then the new concept of technology, and then that inspires new applications of new ideas. But sometimes I'm struggling because I'm really working on the fundamental level of the new materials. And I do find sometimes it's difficult to really get the material to the device side, to like, a technique side. I just wonder, so from your perspective, how do you see the development in material science, and how critical you think they are, and how critical we should have the cross conversations between technology and materials?
I think that's a very good question again, Jenny. Thank you for that. I think this is obviously a very important issue for material science, actually. But I mean, for me, it comes down to whether a piece of research is development driven. Is it driven by technology development, or is it driven by multidisciplinary, the realization of multidisciplinary opportunities, or in fact all three, obviously. But I mean, it's clear from the history of material science that there are many areas where an innovation, in material science has led to really almost an infinite number of possible developments, such as nanotechnology, for example. And that then, it's a slow process, but that breeds, TRL level 4, 5, and 6 projects gradually as time goes on, usually with industrial collaboration. So what you're saying is, could you see the TRL 6 in advance? And the answer is yes, of course you can. If you are a multidisciplinary researcher, you should be aware as a material science of that aspect of the possible development, I think, of your research. You may not get it right because it's crystal ball gazing, but if you get something to TRL level 3, which is proof of concept, then you're very close, I think, to understanding what its potential implications may be. So in this case, the two technologies that came together obviously were touchscreen and infrared time of flight tracking, like such as that of the Kinect or the leap motion device. Without that, it wouldn't have been possible, and without them being relatively advanced technologies, relatively cheap. But it's also the case that when we discussed it, a strong motivator for JLR, for example, was the use of three-dimensional holographic displays, and indeed using in conjunction with haptic devices, for example, so that you could locate the haptic device as a button in the same three-dimensional space as a holographic display, using three-dimensional intent-based process to realize what the user was trying to interact with. I personally still think that's my dream for this area of research, and I can see it clearly, even though it may not be technically possible at this time. You're still muted, Jenny.
Thank you very much. Thanks.
So yeah, good news anyway. It's good news that we have material scientists who are interested in these things, I think. So that's great. In general, the more disciplines, the better.
Yeah, because for me, I had discussions with people from different fields, just discussing about what a new materials and what a new nanomaterials can change the field. And because I'm just talking, well, because of COVID, can't really go to lab. And then the feedback that I got is that I need to be really careful to not spread myself too thin, because from material side and go to different field is like, for every different field is quite a lot of work. So
yeah, I mean, I think you can look. I mean, one thing I would say, this is purely driven by my experiences at Cambridge, is of course the Engineering Design Centre was the seat of Mike Ashby, who you will know, of course, being a material scientist. In fact, he had an office next to me for many years, and I mean, you can see the huge developments that were made by his work in material science. And I think one of the great things about that was that he was that close physically to us working in the Engineering Design Centre that there was many areas in which collaboration could occur outside of material science, not just for the grantor work, which of course is world famous, but many other areas as well, such as blade design for Rolls-Royce aero engines, and you name it, a number of other areas. I mean, certainly there was work in nanotechnology and carbon fiber, not carbon fiber, but the single layer carbon technologies. All that was channeled through the EDC. So that's good. I think that's the sort of way we will hope to go in the future.
yeah, thank you very much. I think I'll probably get in contact with you if I have further questions or.
Yes, please. Thank you very much. Yes, thank you though.
So thank you very much. Does anyone else have any more questions? If not, we would like to thank to Professor Langdon and also for his excellent work with CAPE on CAPE projects. Yeah. And yeah, we are hoping we will be able to collaborate again in the future on other projects.
Definitely. I'm working on that. Thank you very much, Denise. Thank you, Dapeng. Thank you to CAPE. It's been very good. Thanks very much.
Yeah, thank you very much, everyone. Bye-bye.